Hi, so my name is Bill Buchanan, and I host a podcast on the world leaders in cryptography. And today I'm with a true world leader, Jens Groth. Hi, Jens.
Hi, Bill. Pleasure to be here.
Good. Jens is a chief scientist at Nexus and works in many areas of cryptography, including in pairing-based cryptography and zero-knowledge proofs. He was previously a professor of cryptology at University College London. In 2016, he published a classic paper on the size of pairing-based non-interactive arguments, and which defined a zero-knowledge proof based on pairing-based cryptography. This is now known as Groth 16 and is used in many applications, including within Zcash and Tornado Cash. In 2021, he won the IACR Test of Time award for the paper Simulation Sound Non-Interactive Zero-Knowledge Proofs for a Practical Language and Constant Size Group Signature. And then in 2023, he won another IACR Test of Time award with Amit Sahai for the 2018 paper on efficient non-interactive proof systems for bilinear groups. Okay, so what's your current role and what does a typical day involve for you?
Yeah, so now I'm the chief scientist at Nexus. Nexus is a startup company based in San Francisco. And the overarching goal of Nexus is to build verifiable computation at internet scale. Our recent focus is sort of like on verifiable finance. And what I do at Nexus is basically I do research. So we are building a CKVM. So that's sort of like concrete zero knowledge proofs that we're building. We have a compute network that can parallelize these proofs because it's very expensive to compute these proofs. You can bring down the latency by parallelizing the proofs. And then we leveraging this to sort of like build verifiable finance. So think of financial transactions, the financial systems you interact with. We would like to sort of like base them on secure foundations. So we're using blockchain technology. We're using zero knowledge proofs, and the intention is that we want to, make all the transactions verifiable, that you've seen it being processed the right way. Can also imagine sort of like more global, that you know that the financial system you're interacting with is sort of like doing everything correctly.
Mhm. And this is all at layer one. I mean, a lot of work is going on at layer two just now, but you're really interacting with this lower layer of Ethereum, of the Ethereum virtual machine. It's really quite interesting. I'll come back to some questions on that too a little bit later. But what were your school days like? What were you like at as a school pupil?
Oh yeah, that's a long time ago. So so I certainly liked so like I guess you could say that my career is very math oriented, and I did like mathematics in school. I liked physics, chemistry, so the scientific topics I liked a lot. And yeah, and then outside school I was playing chess. It's so like interesting question, there's some speculation research, does what does chess do to sort of like shape your brain, right? And so it's interesting question whether that had an effect. I also played a lot of football, in our yard at home, so that the grass was completely worn down because we were playing so much football back then.
And where was home then?
So yeah, so I grew up. I was born in the Faroe Islands, but we moved to Denmark when I was 7. So most of my time in my childhood was spent in Denmark, in Aarhus, which is the second largest city in Denmark.
Yeah, it's an amazing country, Denmark. They really punch above their weight in terms of innovation and education and so on. What makes Denmark so special?
Yeah, it's something that people have been thinking about. I know that economists have been looking at Denmark and the Scandinavian countries as an interesting example where you have fairly high taxation and still things seems to be going pretty well, so like for businesses and so forth.
Mm.
And one of the things they pointed to is that there's a, you know, there's a high degree of political stability in Denmark, which means it's a very predictable society. I think it's so like um, it's a social democratic society, so there's a fair amount of support for people, and particular universities are reasonably funded, and there's also support for students to go to university. So even if you come from a poor background, then there's still financial support that you can go to university. But I think, yeah, probably the political stability, and I don't quite know so like what the historical reason is why Denmark and the Scandinavian countries are particularly stable, politically speaking. But I think that's seems to be one of the factors in sort of like the financial success of the Scandinavian countries.
Yeah. And so what sparked your interest in cryptography? Well, how did you get to where you were with your studies to work in cryptography? If you could maybe just outline that route from Denmark to where
Yeah,
you are
yeah,
now.
yeah. Um, so I always liked math. So I went, to university. I studied math. So studied a lot of other topics. I did philosophy and physics and computer science and all sorts of other things at university as well, chemistry. But it was really sort of like the mathematics part of it that I stuck with. Um, and at some point, like 2, 3 years into my studies, I got a bit disillusioned with the abstraction level that there's in mathematics. I kind of wanted also to do something that, is applicable in the real world. And I felt it was getting a bit too abstract, the kind of things I was working on. And I took some cryptography courses and found those to be really interesting. And then I decided to pursue that further. So I did a master's degree, I did a PhD. And one
Where was this?
interesting thing, yeah, so one interesting thing about that is that the thesis advice I picked for my master's degree, I mean, I just picked, well, here's a cryptography course. This is interesting. Let's see if that professor is willing to work with me and so forth, right? And I was oblivious that, so this is Ivan Damko. He's like a world
Mhm.
famous cryptography writer, like, has
Yeah.
done amazing work. So it's the kind of guy that people seek out and from all over the world, you get, messages, kind of come and work with you and so forth, right? And I was completely oblivious to that. I mean, it could have been, you know, him, or it could be somebody who just had no sort of like strong track record in cryptography, but just taught that course, right? So I was just really lucky that that I ended up with him as the advisor, and ended up in a university where the cryptography is such a strong discipline.
Yeah. I think he created the MD construct for hashing
Yeah, the
methods.
American Damgard construction is indeed for him. Yeah.
Yeah, yeah, that's great. And so it's a bit like picking your favorite child, which is really impossible. But for all the areas that you've studied in cryptography and all the things that you apply, what's your favorite area overall?
Well, I mean, I've sort of like dabbled in different things in cryptography, but I think the one constant part of it has been the zero knowledge proofs. So when I first did my PhD, I was working in voting schemes, but it was sort of like the zero knowledge proofs used in voting that I was working on and improving. And then I stuck with that part. So I used zero knowledge proofs in the context of mixed nets. I've used zero knowledge proofs in context of digital signatures. I've used zero knowledge proofs, so like just for the sake of zero knowledge proofs. And that's the thing I really, has been like a line throughout my career, that this is something I've been working on. I'm very much a specialist, right? I mean, some cryptographers go and scientists, right, go very wide and dabble in many different areas, and others are like really focused in a narrow something. I'm clearly in that latter category, right? I'm a specialist, and I've been, interested in zero knowledge proofs throughout.
Yeah. And obviously you have digital signatures, which is almost like a zero knowledge proof of a private key. And
You
zero
could say
knowledge
so, yeah.
proofs have become more generalized. So this is a really difficult question. And I was asked it recently to explain what zero knowledge proofs were. I could explain the very simple one, like the Alibaba cave and so on. But I really struggled when it came to actually explaining all the nuances of a ZK snarks and so on. So, what would be your explanation of a zero knowledge proof?
Yeah. So okay. So zero knowledge. knowledge proof is, so a proof, right, is something where you can convince somebody else that a claim is true, right? So the core property should be possible to convince somebody of something false, right? It should really be when things are true that they get convinced. And then the zero knowledge part of it is that you're not disclosing anything except the fact that it's true, right? So it's sort of like one bit kind of transfer that, yes, this is true, and then you're not disclosing anything else. And this is something that's very surprising to people that that can even be done, right? Because if you see other types of proofs, say mathematical proof, right, then good mathematical proof is one that explains as much as possible, right? So it's sort of like the reverse. You're trying to give as much information as possible rather than as little information as possible. So it's very surprising that this can even be done, right? And this was something that was discovered in a classical paper from the 80s that you can do zero knowledge proofs. Um, I usually give an example to people when I explain this, just to give an intuition of how that can even be possible. So my example is I take a deck of cards and say, let's, I'll pick a card and I'll say, okay, make some sort of like claim about it. Like, I'm holding this card. It's a seven of hearts, say, for instance, right? So maybe I'll say, this is, you know, one of the hearts, right? And of course I could show the card and then they would know that it's one of the hearts, but then they would know specifically that it's seven of hearts. So I've sort of like disclosed more information that the claimer was making, right? Okay, so but instead of revealing the card and showing them that it's a seven of hearts, right? If I just want to convince them that it's one of the hearts, not disclose it seven, what I can do is that I can take the remaining cards, right? I can show them all the ones that are not hearts, right? So now I'm left with the card I'm holding in my hand and 12 other cards that's on the deck, right? And they know that all of these cards must be hearts because they've seen all the other cards, right? So that sort of like reveals that, hey, it's one of the hearts, but it doesn't reveal which of the hearts it is. So that's the example I usually use to sort of explain that this is even a possible thing to do.
Yeah. But obviously, with ZK snarks and starks and so on, the explanation is probably too difficult to find a simple explanation,
Yeah,
I
you
would
know what?
think.
Yeah, I think then, I mean, if it's for an audience that sort of like needs some more details, I usually think
Mm.
of this as zero knowledge proofs that have different parameters, right? So you could be interested in, how much data am I sending when I'm sending a proof? How many messages do I need to send back and forth? Because these can be interactive proofs, right? So that's all like, typically a challenge response protocol, right? Where there's a prover that, sends something, there's a verifier that sends a challenge back, and then the prover responds to that challenge, it gets another challenge and so forth, right? So there's a question of how many messages go back and forth. There's a question of like, how much computation does the verifier need to do to verify that the proof is correct, right? And there's a question of like, how much computation does the prover need to do to compute all these messages along the way, right? So you can think of all these performance parameters that are in a proof. And then a lot of the, special nomenclature really just is a question about, combinations of these. So for instance, a snark, right, which has become a standard term, right? It stands for something non-interactive argument on knowledge. What it really says is that, first of all, it says it's non-interactive. So that means there's only a message from the prover to the verifier, and then you're done, right? So that's the simplest possible interaction pattern. Okay, then it says it's succinct, right? That means the proof is really small. So even if it's a very complex statement, right, that would require, I don't know, billions of uh, bytes of data and lots of computation and so forth to verify, then the proof itself is going to be really, really small, and it can be down as to a few hundred bytes. Okay. Okay, and then there's typically also some requirement here that the verification complexity shouldn't be high. It should be sort of like fairly easy to verify, right? And that's a snark. Okay. Sometimes people distinguish between snarks and ZK snarks. ZK means it's also a zero knowledge proof. So it doesn't disclose anything else that, that this claim is true. And another type of this is a STARK, which stands for Scalable Transparent Argument of Knowledge. And a STARK is a special type of SNARK, which, again has some specific uh, properties. So I think a lot of these, there's a lot of different terms and abbreviations people use for different combinations of these parameters. But I think most of it really is about, core is you have a zero knowledge proof and it has some specific parameters, right? And what are those parameters and where can you land in that parameter space?
Yeah. It was obviously Fiat and Shamir who actually showed how we can take an interactive proof where you send a challenge. I think we would define uh, Peggy and Victor. Peggy is the prover and Victor is the verifier. So in a interactive proof, Victor sends Peggy a challenge, C, does
Yeah,
something with it, and then sends it back. And then Shamir came up with this method where we could hash a few things together, create a random nonce value, and then send it back. It's almost like magic, and I think it still feels like magic that you don't have to be told about something, but you can actually prove that something is the case. I think you give a great example there. So if we go back to your company, so you moved from academia into your company. So could you just outline what the Nexus product is and what is their vision?
sure. Yeah.
Mm,
So as I said, at Nexus, we're trying to do verifiable computation at sort of like a very large scale. And the vision is that, the whole world, all data will be, come with proofs and be verifiable. So it's trustworthy data you have rather than just random data where you don't know whether you can believe it or not, right? Um, and the question then is, okay, so these proofs are expensive to compute. So you can ask sort of like what are sort of like the primary areas where you would want to go first and where you would be willing to pay that price for computing the proofs. And I think one such area could be finance because there you actually have transactions with high value, right? And what we have seen is that there's been a lot of interest in the blockchain space for zero knowledge proofs. Um, so yeah, so that's what we're doing at Nexus. So like from a sort of like grand vision perspective, and concretely what we're doing is we're building a CKVM, so a particular tool to create proofs. So the idea is that think of a cloud service where you want to run some program, right? And then you get some result back, right? And is that a good result or not, right? So a CKVM allows you to compute something, but also construct a proof that this computation really is correct and that it's the right output of the program. Um, so we built a CKVM, and then yeah, we're sort of like leveraging that as a tool to build other things
yeah,
and essentially try to inject proofs in everything that we do.
yeah. And an EVM is an Ethereum virtual machine. So you're using the Ethereum model, a layer one, which is obviously a challenge to be able to scale that up so that would match
Yeah,
with Visa and so on. So it's really quite a challenge for you. When you think that our PC architectures, our Intel architectures have been running for decades and they have no trust in them. We have no trust that any computation is correct and has it been modified or looked at or anything. So I think what you're trying to do is amazing, and it's really probably trying to create a computer that is correct, that you can actually, I can give you a
exactly.
computation,
Exactly.
you can do the computation for me, and you give me a little receipt back to say, yeah, I did it for the inputs and the outputs. Here is my proof of computation. And I know that that is one of the biggest challenges in computer science at the current time. So, what do you
Yeah.
think the future of finance? I mean, I see stable coins happening and I see tokenization eventually happening. In the UK, we might even have a digital pound. In China, the US, we have stable coins and so on. So you really feel that the finance industry is starting to move on tokenization properly to get cryptographic signing for tokens and so on, and we'll move away from our fiat currency, our paper-based approach towards a new world of finance. So what do you think the future of finance is, and what will digital money look like?
Yeah, so I mean, so one of them is the digitalization of money, right? That will move away from, say, paper money, right, to digital money. And I think that's already, well on the way, right? I mean, you pay with credit cards online and so forth, right? So I think that's a given. But I think the more important part here is the trust that you have in these systems. And I mean, we're so used to, fiat money, right? But I mean, there's a lot of trust built into that, right? So people used to use the gold standard, right? What is the
Mm,
advantage of gold? Well, it is a finite resource, and typically what happens in price is fairly stable, and the reason it's fairly stable is because if the value of gold increases because there's more demand for gold, then the incentive to mine for more gold and dig out more gold increases, right? And you sort of like have this system that goes into some equilibrium. Um, and then at some point we moved in the 70s, we moved away from the gold standard. Um, and I think there's a huge risk with that, right? Because it does give freedom now to a central bank or to politicians to sort of like print more money and increase the inflation and reduce the value of people's savings, right? And we've seen that, right? So, I think people that come from a country where that didn't face those problems, they're pretty happy with the fiat currency, right? But you have plenty of countries where, things go haywire and suddenly you have like hyperinflation and the value of your money is basically gone, right? So you see countries like Turkey right now, which has very high rate of inflation, for instance, right? And it creates real problems for people there. It's basically you have money, you have to go out and spend it now because the next week will have lost some of its value. Um, so I think the really nice thing about cryptocurrencies is that you can build technology that really tries to take the control away from people and build it, that kind of control the amount of currency from a technical perspective, um, which makes it more predictable, means that you can't have somebody who sort of like tampers with the supply and changes the value of it for whatever their purposes are. And I think there's also a value that it is a technology that can sort of like make this accessible to everybody, right? So there are people that can't get access to bank accounts for whatever reason, right? And I have to say one of the values of say gold, for instance, or so like traditional paper money is that anybody can use it. I mean, it's also like the bad guys and criminals and so forth that use it, right? But it's also part of the value for all of us, right? Is that everybody can use it, right? And I think there's also some opportunity for cryptocurrencies to be accessible to everybody. Of course, there's sort of like a battle going on there, right? I mean, there are also regulatory entities that is trying to restrict access to cryptocurrencies. Um, so I'm very much a fan of cryptocurrencies. It wasn't something before I went into the space that was that big a fan, but I have become a fan, and I've probably become a fan more because I'm skeptical of traditional fiat currencies than because I think everything is great. I do think we have a lot of work to do still on cryptocurrencies to create the right system, but I do think that's it's a more sound technological structure. It's a more secure construction. So I think this is where we ought to go. And on that note, I would say I'm also not a fan of stable coins, right? Because that's essentially trying to tie some cryptocurrency to, again, central bank or something like that. And I don't think that's the right way to go.
Yeah, it's a question that's open just now, and I know the central banks are trying to pull back their currency because they see their currency devaluing. And there's a whole thing about wholesale payments and so on, where banks are transferring money between each other, and they're still transferring fiat currency. There's lots of fees involved, and it takes a while. and it just seems crazy that we're not implementing these things with smart contracts overall. So it's an interesting time, and I think there is a place for all of these technologies, and I think you've just got to find the application. And certainly, stablecoins are a thing, and I can see them. Commercial banks probably are finding them easier to deal with than cryptocurrency. So I think we just have to see where we end up overall. So you work in all the difficult areas of cryptography that are really difficult to explain zero knowledge proofs. And then we have the magic of pairing-based cryptography. So I've talked to Jan Kamenisch, who used to create amazing papers that had privacy-aware identity and sharing and so on. It's just the way that pairing-based cryptography is actually used is just fantastic. So this is a really difficult question too, but could you explain what pairing-based cryptography is and how it's used?
Yeah, so I certainly can't explain the technical details in here, but
In
I think
here,
I
yeah.
may be able to convey some sort of like where the power comes from. So and and so there's and for a long time people have used cyclic groups
Mhm.
to construct cryptography. So there's a lot like Kamal signatures, DSA, and so forth. They all rely on groups where essentially what happens is you have a secret exponent, right? So you have a group element. What is that group element? Well, it's some generator raised to some secret exponent. What happens
Discrete
if you
logs,
multiply
typically. Yeah.
two group elements? Well, it corresponds to adding these
Mm,
secret exponents, right?
mm,
So now you have the power of addition
mm.
of some secret values. Okay, and that turns out to be really powerful. And you could build a lot of interesting things like the Gamal encryption scheme and so forth based on that. What pairing-based cryptography does, it introduces another mathematical operation. You do a pairing of two group elements. And really what happens under the hood is that now you have two secret exponents that get multiplied together, right? So now you have the power both of addition, but also the power of multiplication. And that turns out to unlock a lot of new things you can do. So now you can build some other variants of digital signature schemes. And it turns out also you can do zero knowledge proofs with these pairings. So just that kind of like added thing that I can do both additions, but now I can also do a multiplication. It gives you much more leverage to sort of like design cryptographic schemes. And really that's where the power is coming from.
Yeah. And it scales very well to elliptic curves. I mean, obviously, we started with discrete logs. The pairing of g to the power of x with g to the power of y can become g to the power of x, y,
Mhm.
g. And we
Yeah.
can move the exponents over. And then with elliptic curves, we have AG, where G is the base point, paired with BG. And then we can have ABG paired with G, our base point. And you can do some really amazing things when it comes to privacy overall. I suppose the one problem just now is that we haven't found, as far as I can tell, a quantum robust method. I may be wrong in this. Maybe they've been working on lattice methods, but that's an open area just now that we've got 10 years perhaps to find a solution. I don't know if you know of anything that would work just now.
So, I mean, so we do have techniques, in particular something like lattice-based cryptography, which actually gives you even more power, right? So you can, now you can have cryptography where you sort of work on secret values and you can both add and you can multiply them. But actually, pairings, you can only multiply them once. With lattice-based cryptography, you can have many multiplications and you can even build fully homomorphic encryption where you can encrypt pieces of data and you could do any computation on these secret pieces of data without disclosing, anything from the computation, right? And get a ciphertext that has some result of a computation. So I think this is really amazing. It's a little harder to work with, and the reason is that group elements are like really clean mathematical objects. And typically in lattice-based cryptography, what you have to do is you have to add some noise. And this is sort of like where the post-quantum resistance comes from, right? So you can sort of like show that in general there are quantum algorithms that can break things where you have this kind of like a clean group structure. So you need to do something else. And what you do in lattices is you have some noise that you're adding that sort of like make it hard for algorithms to figure out what's going on under the hood. But then, you have to deal with that noise, and that also adds a lot of complications and makes things not quite as clean as in the group setting.
That's right. So we're using learning with errors, which is A, which is some sort of matrix times S, the secret, plus E, which is a small amount of error. And we can represent these typically as polynomial values with a high order. They're roughly vectors. And as you say, vectors can be multiplied, added, and so on. And it's quite amazing, as you say, you can now take any primitive and actually start to do a homomorphic circuit. So rather than most people think homomorphic encryption is integers and floating point values, but with some of the most recent work, you can actually build any circuit that you want. So the answer to that question was fantastic. So we have opportunities. We just need to build the circuits that would allow us to be able to implement what we have just now. And you're right, we can build any circuit. Where pair-based cryptography was limited in what it can actually do with homomorphic encryption, then we can have so much. And you've contributed so much into that area. We'll come back onto that in a little minute. So, what's the future of blockchains in using non-interactive zero-knowledge proofs, and what do you think the main application areas are?
Right. So I think what we're seeing now is that zero knowledge proofs are really being integrated into blockchains. They have the potential. So let me try to give one intuition of why this is powerful. So traditionally in a blockchain, you would sort of like have blocks of data. Whenever you sort of like go to the next block, you can do computation on that data and agree, hey, the result and the new state after all processing all these transactions in the block is this next state, right? And you would then take all that data, right, all these blocks, you would distribute into a bunch of validators and make it all public so anybody can verify that. Okay, but that also means you're doing a lot of recomputation, right? Because anybody who looks at a blockchain, they sort of like have to start from the genesis block, process all the data, and double check that everything has been computed correctly. So what zero knowledge proofs allows you to do is to take that computation offline, right? And one idea that people are thinking about now, this is sort of like behind things like roll-ups and validiums and so forth, right, is that what you want to do instead of processing data on the blockchain and have everybody recompute it, what you can do is you can off-chain say, hey, I have a bunch of transactions. If I process those transactions, this is the new state, okay? And then you can prove that this would be the new state processing these transactions. And now you give that proof to the blockchain, right? And say, here's the new state, here's a proof that this is a correct new state. And now what you have to do in the blockchain, and when you have all these validators that are double checking the blockchain is doing the correct thing, they just have to verify the proof. They don't have to do the computation to compute the next state. You just need to get the next state and check a proof that this is the correct state. Okay, and this is where then it's key that this is, say, a snark, right? That you want this proof to be succinct, because if it's very small proof, then it's easy to store in the blockchain, right? If it was a giant proof, then there will be a lot of data and very expensive to store in the blockchain. Okay, and you want it to be easy to verify, right? Such that the computation you do is much less than if you had to recompute all these transactions and see this as a resulting state, right? And if you have those properties, right, then you get something which is a saving for all of these validators. So that means you can take computation offline, and you just sort of like what you put on the blockchain is just the stuff that you need to verify, right? And that in turn means that now you can also scale up the kind of amount of throughput you can have in the blockchain, because you can have even more stuff that you process because these proofs are very simple and compact and easy to verify, right? So you basically have a larger computation that is simple to, and just have like a simple to check proof that everything has been processed correctly. So
I,
this is like a really powerful full tool, and it's all like very exciting to see how blockchain and zero knowledge proofs are being integrated with one another.
yeah, and you see companies like Nethermind and Polygon who are existing in the layer two Ethereum. So they're building on layer one, rock solid security that isn't struggles to scale up. I know that your company is scaling up, but obviously the typical Ethereum infrastructure is that you can only do maybe 10 or 20 transactions per second. But then the magic happens at layer two, where you create these Z key roll-ups, as you said, where you take transactions
Mm.
offline, then roll them up.
Yeah.
You can either do an optimistic roll up, as far as I can tell, which you might have a fraud in there later on, and it might get locked for 30 days for a transaction, and you need a lot of checking from arbiters and so on. To a world that is almost instant, I can put my transactions back on the ledger in an instance, and then I can give you a proof that these are all correct. It's again, it's just like magic to me, and uh, we spent so long in layer one, kind of looking for creating islands and making everything quite complex. But actually, the solution for part of it, and certainly for Polygon, because they can really increase the rates up to near finance type levels. It's really quite interesting. So for your classic paper on the size of pairing-based non-interactive arguments, what was your main focus for that paper?
Yeah, so there's a bit of a history for it. Okay, so let's see if I can sort of put the contribution of the paper in a nutshell. Um,
Mhm.
so what it does, it creates a pairing-based snark, which is really compact. So
Mm.
the proof that you construct in that, and it could be proof for anything. Okay, but the proof is just three group elements. So we'll talk about a few hundred bytes, right? And the reason it's so popular in the blockchain space is because this is all like state of the art. It's all like creating the smallest possible proof. So you can store it on the blockchain at just a few hundred bytes. So it's, the cheapest proof you can put on the blockchain, right? And let other people verify. So this is why it's become very, very popular. Um, so interestingly, what my focus in the paper, I mean, one was sort of like having this construction. There's another half of the paper which is also trying to look at what is, could you do something even smaller than that, right? And trying to establish a lower bound. And I got close. I got proof that you cannot do proofs with less than two group elements. It's still an open research question whether you can do pairing-based proof with two group elements. That we don't
Mm.
know. If I had to make a guess, I would say no, but I don't have a proof for that.
Difficult, yeah.
Uh,
So what's Groth 16 and where is it used?
So yeah, so it's used a lot in different parts of the blockchain, right? Because it is such a compact and small proof, so it's just easy to stick in there. If you think about like a modern way of doing zero knowledge proofs, typically what a
Mm.
zero knowledge proof is nowadays is actually composition of many sub proofs. Okay. And the reason is that there are different things you want to optimize, right? So one thing is you want the size to be as small as possible, but then the problem is that they are really expensive to compute these proofs. So you want to minimize also the time it takes to prove something. Okay? Now, Groth 16 is very small and compact, but it doesn't have the best of the prover times, right? So you would pay an overhead for that if you just used Groth 16. So what people do is they start with a proof system, which is very efficient for the prover. And, a bit, it gives you something, so like on the proof size, so the proof is not, enormous, right? It sort of like reduces the complexity, it's easy to verify, but it doesn't push it all the way to the limit. Really, what you want to optimize for is the prover time, okay? So you have like, say, a large computation, some claim you want to prove. You use a very efficient proof system from a prover perspective, prove that first. Okay, and now you have sort of like this intermediate proof which is more compact, which is easier to verify than doing the computation itself. Okay. And now you use a second proof system, say Groth 16, right? That, and prove that if you verified this first proof, then you would have, you would say, yes, this is a good proof. And that then squeezes down like the size and the verification time to the absolute minimum, right? So now you have the best of both worlds. You have like something that's reasonably efficient to prove, and it's very cheap and very compact to verify. And you can have several layers of these kind of, proof systems where you start with something that's really efficient for the proof, and then you sort of like squeeze and squeeze and squeeze, and you may wrap up in the end with something like a Groth 16 proof that so like does the final squeeze and really gets everything down in size. So you have these pipelines now of interconnected composed proof systems, which is what people use in practice.
Because I suppose you've got to watch that someone doesn't create a new method that has some sort of weakness that hasn't been checked. So to be able to check in the end to know that something is correct, it's not necessarily the smallest, but it's like creating a hash value. You
Mm.
do have to go and check it against OpenSSL to make sure your hash value with the salt value is correct and so on. So that makes a lot of sense. It's almost like proving, and then at the end you have this overall proof that everything is definitely secure. And it does no harm to keep proving all the way to the end. So
Yeah.
you've worked in many innovative areas. So one is obviously a shuffle. So you have a shuffle of cards. I give you the cards, and you will do a shuffle, and then you will prove to me that the shuffle is correct. What do you mean by correctness there, and how can I actually prove that the shuffle is correct?
So this is something I did, and this is many years ago when I was a PhD. I started looking at shuffle proofs. I thought they were really fascinating objects. So the general theme is that, say you have some encrypted values. You have two sets of encrypted values, and how can you prove that? So like the second set contains the same values as the first set, but perhaps in permuted order, right? And as you said, this could be used to prove a card shuffle, but it's also very used in mixed nets, where the idea is that you want to enable people to sort of like publish messages, but in a private manner, right? So this could be used in voting systems, for instance. So, and there, what you do is basically you encrypt your message, right? And then the service would pool together many encrypted messages, and then you can sort of like permute these ciphertext, and it may randomize the ciphertext, so you can't sort of like link one ciphertext from outgoing ciphertext to an incoming ciphertext, right? And publish these outgoing ciphertexts. Okay. And the problem then is that, well, if that service is honest, then you get a permutation of the previous messages. But if it's dishonest, then you could just you know throw out some of the ciphertext, right, that came in, and just put in its own messages encrypted form, right, and output that. So it might not be correct. And for that, you can then ask the service, to prove that it has done a correct shuffle, right? So all the original messages are there. They're just there in a muted order. So this was a problem, so like a special type of statement that you could want to use in prove in zero knowledge, and I did a lot of interesting work in that area, trying to sort of like increase the efficiency of those proofs. And back then, this was sort of like the frontier of like what it was feasible to do, right? So nowadays the frontier is like we want to prove very general types of computation and so forth, right? Back then, proving that a shuffle is correct was a computationally expensive operation, right? So the game was the challenge was to develop technique that would be efficient to prove that shuffle is correct.
Yeah. And I've seen some really interesting work, typically using Elgamal encryption, where you could take, I don't know, 52 playing cards. You then encrypt every one of those playing cards. And then what I can do is I can create a shuffle, but I can also encrypt them again. So you can't link any of the encrypted values that went in to any of the output values. And I can see lots of applications for that type of thing. How do I know that the playing cards are still there, that you've not cheated and
Yeah.
actually created random cards and so on? So there's some really interesting, and I suppose it is a zero knowledge proof application
Yeah, yeah,
overall
sure.
that's quite specific. So what's a perfect non-interactive zero knowledge proof for NP?
Okay, let's see. So first of all, I don't know if all of your listeners are familiar with NP, so it stands for non-deterministic polynomial time. Um, and roughly speaking, polynomial time is a term that theoreticians use for things that are efficient to compute. So if you have a claim which is in P, it means that you can take your computer, compute on it, you can figure out whether it's a true claim. And NP is sort of like claims you can verify if you have some witness, some extra advice that helps you to determine that, right? And this might be confidential piece of data, so you may not want to disclose it, right? So what you can do, well, if you want to convince somebody that a claim in NP is true, but you don't want to disclose the data, well, you can give them a proof, right? And if it's a zero knowledge proof, it doesn't disclose the data, but it does tell them, hey, there's some advice, and if I had that kind of advice, then I would not be able to verify that this is really a true statement. Um, and it's very general, so you can prove that, any computation can be efficient computation can be used to a language in a claim in which is in a language in NP, right? So there's a like universal type of computation you can do in principle when you can prove things are in NP languages. Okay, so let's see. So let me go back so like to the history of zero knowledge proofs. So they were invented in mid 80s, and very soon afterwards, people were thinking, okay, what is the minimum amount of interaction I need to prove something? And they came up with non-interactive zero knowledge proofs, right, where it's just like the prover creates a proof and then says, here you go, I'm done, right? And then the verifier can verify that proof. Okay. So we knew in theory that could be done, okay? But they're really, really complex constructions. Um, and an alternative was the Fiat-Shamir heuristic. So that came afterwards, and that's efficient. But then people have not really figured out a good way to reason about the security of the Fiat-Shamir uh, construction, right? So the question really is what if we want to sort of like take standard reasonable cryptographic assumptions and build non-interactive zero-knowledge proof from that? Okay, so there were constructions, they were complicated, okay, and they also had a bit of a trade-off in the sense that they could have very strong soundness guarantees, okay, so you can't cheat, you can't prove a false statement, but weaker privacy guarantees where you really depended on a cryptographic assumption for privacy. It's all like akin to encryption, right? That, the data is there. We're just assuming that it's hard for somebody to get out what the plain text is unless they have the secret key. Um, so you could ask the question then, could we get like the sort of ultimate privacy guarantee, right? Could we get, perfect zero knowledge that, regardless of how much computation, then an attacker has, then they can't get out the secrets underneath, right? We know there's a trade-off, so, then you would have to base soundness on computational properties and assumptions. But that was like a very interesting question from a theoretical perspective, right? And I spent a fair amount of time thinking about that, and the techniques just didn't really seem to work for that. And then I was at a conference, I think this was TCC Theory of Cryptography Conference in 2005. And there was this interesting paper on encryption that was using pairing-based cryptography. The Bonnet-Goanism from 2005, right? So they introduced an encryption scheme. And when I was looking at that, I figured out that, hey, it seems like you can actually construct a non-interactive zero-knowledge proof from this, okay? And not only can you construct a non-interactive zero-knowledge proof from it, if you set the sort of like the parameters right, it actually has perfect privacy, right? So perfect zero-knowledge, okay? With no so like assumptions, it's just guaranteed unconditional that, it really is private. So that was like a very interesting, so like a theoretical breakthrough, right? Really enabled by this new, back then it was a fairly new, so like technology pairing-based cryptography. So that's sort of like the origin of how we came up with, doing these proofs. And what was really interesting then is also that it was a much more efficient scheme than the previous non-interactive zero-knowledge proofs construction. So it really is a simpler construction and so like something, eventually in future works, we saw like improved on the efficiency and got something you could use in practice.
Yeah. Well, I think it was Shafi Goldwasser who first proposed the potential of zero knowledge proofs in, was it the 1980s at
Yeah, yeah.
MIT? And then obviously there's for for the advancements of that the so cryptography itself often involves the usage of random oracles. So how is it possible to create a fully anonymous group signature without using random oracles?
Right, yeah. So, okay. So let me see. So to provide a bit of context, right? So digital signature says, okay, I can construct a public key. I know the secret key that corresponds to that. Nobody else knows the secret signing key. And now I can sign messages. Okay. And people who have the public key that can see that signature, then can verify that signature on the message. And because I'm the only one who has the secret key, I'm the only one who can create signatures so they know that it's coming from me and I authorized this message. Okay. Now you can build a lot of so like variants of zero knowledge of digital signatures with various properties, so advanced digital signatures. Okay. And one particular variation of that is instead of saying that, that person signed something, you might say somebody from that group signed something,
Mm.
but without disclosing who it was from that group. Okay. So that's like one variation. You can also then have, okay, properties like, well, but maybe in some cases we need to figure that out. So there should be some authority that can sort of like disclose, if you've really sent an abusive message that, oh, it really was that person, how we should go and punish them. So that's sort of like what is called a group signature, right? But you have this property that it's anonymous who in the group is signing something. You just, when you see a signature, you just need know that it's somebody from that group. Maybe it's an organization or something like that. You just care that it was somebody from IBM that signed it, but not who it was in IBM that signed it, right? Um, and so so this is something then that people started building, and there's been a lot of research in how to design these kind of anonymous groups signatures. And the standard way is roughly something like this. So you will, when you want to sign a message, you will sign it with like a standard signature scheme. You will encrypt it under the authorities key, right? So now it's so like confidential what the signature is and who created that signature. And then you will prove with a zero knowledge proof that, there is a valid signature from one of the group members inside this ciphertext, right? And now you know that's somebody from the group that signed, but you don't know who it was that signed the message. And the question then is, okay, how can you construct these proofs? Okay, and so like a classical way would be that you pick some encryption scheme and signature scheme, and then you'd use something like the Fiat-Shamir heuristic, which relies on a random oracle model. And people speculating, do they like the security properties or not of random oracles, right? But that sort of gives you efficient group signatures. And then the question is, okay, now we have had these new techniques, right, based on pairing-based cryptography, which could give you efficient non-interactive proofs without relying on the future heuristic and hash functions and so like the random oracle model, right? So when can we start applying that? And it turned out that these new pairing-based proofs, they were also really efficient for like, combining in and tying into other pairing-based cryptography. Okay, so when you have a pairing-based cryptography construction and you use these proofs, they sort of like gel very well and you get some very efficient constructions. Okay, so now you can imagine then if you take an encryption scheme, which doesn't use random oracle, just use pairing-based cryptography, take a signature that just use scheme that just uses pairing-based cryptography. I take a non-interactive zero-knowledge proof that just uses pairing-based cryptography, and you all glue that together. You get essentially the same construction, but without using random oracles at all, right? So it's sort of like based on a completely different type of assumptions and sort of like security properties. So that was really, really exciting to sort of like work on that. And we saw like it became an interesting area in itself. So we introduced this notion of structure preserving cryptography, which is essentially pairing-based cryptography for signatures, encryption, everything else you can think of, okay? Where you try to preserve, so like as much as possible, the mathematical structure that you have in pairings, okay? And the reason is because these proofs tie very well in when there's a lot of structure. Okay, so if you preserve that kind of like pairing-based structure, then you can also construct very efficient proofs for it and tie them together. Suddenly you can build all sorts of things, cryptographic schemes where you sort of like take these pieces and they sort of like fit nicely together. So that became sort of like an area of study in itself, like how do I construct cryptography that's friendly to non-interactive zero-knowledge proofs, and how do I construct non-interactive zero-knowledge proofs that work well for pairing-based structures.
Yeah. And I suppose an example of a group-based signature is in a cryptocurrency where, say, a central bank wants anonymization of a certain group, but needs to make sure that for anti-money laundering, that someone somewhere will be able to identify exactly who it was. So it's
Mhm.
almost like creating a nice balance between the two.
Exactly, exactly.
So, how can fully homomorphic encryption be used to? Because you think of fully homomorphic encryption as requiring a lot of processing power, and maybe with these lattices, we create larger
Mhm.
ciphertexts and so on. So, how can you use fully homomorphic encryption to reduce the size of a non-interactive zero knowledge proof?
Yeah, so I haven't worked too much on fully homomorphic encryption, but I did one work where I was using it really to sort of like with my co-authors to study sort of like theoretical properties of non-interactive zero-knowledge proofs. Okay, so the question we asked there was, okay, suppose I want to construct a non-interactive zero-knowledge proof, okay, which has strong soundness properties in this case, right? So I don't want to really make sure that without any assumptions that I'm guaranteed that there will be no cheating, okay? And you could ask then, okay, how efficient can that proof be? And you can show that if you want strong soundness, then probably you need something which, you know, is at least the size of sort of like the witness to this statement in NP. Okay, so there's sort of like some minimal. But the constructions were actually more complicated than that, and the proofs were even bigger than that, right? And it turns out that you can use fully homomorphic encryption to do that. And roughly the idea, which was already present in Craig Gentry's thesis, so he was someone who sort of like realized that lattice-based cryptography could be used to build fully homomorphic encryption. Okay, so it roughly is something like this. Okay, I will say, okay, I will encrypt the witness with fully homomorphic encryption. Okay, so now it's confidential. It's not public what the witness is. Then I'll use the fully homomorphic encryption property to compute everything I need to compute to check whether this is a true claim about that witness. Okay, I'll get a ciphertext that then says, yes, or it says no, right, depending on that. Okay, and now I can use a non-interactive zero knowledge proof to prove this final ciphertext contains yes. This was a true claim, right? So by combining full homomorphic encryption with like a standard non-interactive zero knowledge proof, I can actually get something which is fairly, like compact proof, right? Because the proof in the end will contain the ciphertext with the witness, and it will have this non-interactive zero knowledge proof, but the resulting ciphertext, which is small, okay, because it just encrypts a yes. Okay, and what we in the work I was involved in, we then sort of like pushed that even further and sort of like realized that, well, if you combine fully homomorphic encryption with sort of like standard symmetric cryptography, then you can actually squeeze that sort of like the auxiliary data all the way down to exactly the witness size, right? So that means that you sort of like have the optimal size of the proof, which is, the size of the witness plus a little bit more. So that was sort of like a nice theoretical result. I mean, obviously, full homomorphic encryption is expensive to compute, so I wouldn't say it's a practical result, but it sort of like showed us like that, in theory, we can reach exactly the limit you would expect.
Mm. Yeah, that's interesting. And recently, the IACR had to pull an electronic vote because someone lost their key. Just shows you that the cryptography is 100% and humans are rather flawed. And I know that you've done a lot of work in the past around trusted voting and so on. What would your approach be to setting up a voting system, say for a country?
Yeah, yeah. I was a little surprised, about this. Okay. So I mean, there's been a lot of research in voting systems, right, and using cryptography to design them. And the Helios voting system that the IC uses is sort of like one of those examples. And I think it's a very sound system, and I think it's a respected system in the field. So what does that show? Roughly speaking, a security model is often something like this. We have some authorities, and there will be the responsible parties for like, when all the encrypted votes come in to tally the result and so like compute what is the final tally and doing that in a way that, you're not leaking any of the individual votes, right? But you just get the result out. And the way you try to set up that security then is that you typically do some key splitting. So you do a secret sharing of so like the decryption key that can extract this final tally. Okay. And you do that in a threshold way, right? So you have, like, say you have 5 authorities, right? So you can then sort of like set your level. Do I want, you know, all 5 authorities to be present and support the decryption, and then I can get out the result, right? That's one thing where you could do it and would have strong privacy, right? But it also means that if any of them, for whatever reason, can decrypt, say they lost their key or something like that, right? Then you'll never get out the result. Okay, you
All
could
or
do the
nothing.
opposite. You could say like, I want to have really strong guarantees I can get out the outcome of the election, so I can set it up so, if just one of them has a secret key, then I can get out the decrypt and get out the result, right? But that reduces the privacy, right? Because now each one of those could, decrypt and maybe also decrypt the individual votes, right? And see what everybody voted. So typically what you want to do is land somewhere in the middle, maybe say 3 out of 5 authorities, right? So it should be there and contribute, and then you can decrypt, and otherwise you can't decrypt anything, right? Because that means that, there's no single authority that can decrypt individual votes and figure out what somebody voted, right? It also means that you have some resilience that even if one or two of them, get hit by a bus and can't decrypt anything, then you can still get out the results. So that's sort of like classical trade-off, right? And you can sort of like, and then think about how many authorities do I want, right, to participate, and what is the threshold? And what happened for IACR was they said, okay, we will have three trustees, okay, and we'll do a 3 out of 3 encryption scheme, right? And now, one of them lost their key, right? And you can't decrypt the result. So it's basically, having a bit of an odd configuration. And I have to say that, I mean, part of these voting system laws, you make everything public and everybody can verify, if I had looked at it, then I would say that's a bit odd. But, I didn't, right? So it also shows a little about, I mean, yeah, cryptographers are as lazy as everybody else, right? And, so it was a bit of an odd setup. And I think then, now they're rerunning the election, and this time they set a 2 out of 3 threshold to decrypt.
2 or 3, yeah, that seems right. And it's perfect security for the 2 out of 3, but the all or nothing, I think that's a Reed-Solomon type approach where you need to get
Yeah,
all your shares. Like when you do it with on a disk for storage, if you've got your hard disks, then you need all of the disks to be alive to recover the
mm,
data. So sometimes what we do is we stripe the data to make sure that if one of the disks was to fail, then it still is allows us to happen. So I think the Reed Solomon is the all or nothing. And it just
yeah,
seems
yeah,
crazy that a cryptography organization would actually do that. But it appeared in the New York Times, I think, so at least gets the topic out there. And IAC are such a wonderful organization overall. They have great credibility in terms of the academic content, the
yeah,
conferences, the
yeah.
peer review process, and there are some really amazing people as fellows overall. So it's just unfortunate, but you can't do anything with cryptography. If you've mucked up, then really you can't recover it
Yeah.
again. So it's really interesting. Thanks for your thoughts on that. In the UK, we still use bits of paper and we still use a pencil and we stick these pieces of paper into a ballot box and then someone comes along and picks them up in a van and goes along. You still have humans uh,
Yeah, yeah.
just we need to just move away gradually. I mean, we're moving towards digital
I think,
identity in the UK.
yeah, I do think that, there's some nuance to this, right? I mean, I worked a lot in voting. And I think the concern is so people have and very competent cryptographers as well have you know argued against using electronic voting. Okay, and a good reason for that, because there are some security things that are hard to get, and particularly it's hard to defend against coercion attacks, right? Where somebody
Yeah,
goes, and if you can vote over the internet from your home, right? And somebody goes with a gun and points it at you, right? Then, you're probably going to vote that way that they want you to vote, right? And you could argue maybe that comes easier than, if you have like a polling place and it's sort of like under a controlled circumstance and you can see there's only one person going in and marking the ballot, right? Um, I do think that here probably perfect is the enemy of good, right? Because it's also like, yes, digital voting systems are not perfect, but then paper ballot systems are not perfect either, right? And there are
no,
lots of clever tricks you can play to, make sure that people actually vote the way you want. For instance, if you think about people going into the ballot box, one scheme that people have used to coerce people there is basically, they will, mark a ballot with the candidate they want to vote it, right? And then give that to you. Now you go and pick up a blank voting ballot, you go into the booth, right? You deposit at the end one of ballot, right? And then you walk back to these guys, right? And what they want is your blank ballot, because then they know that you have submitted the one which actually voted for the candidate they want, right? So you can also do coercion with paper ballots, right? And this is well known. So it's not a perfect system anyway.
no.
And then, yeah, there's a trade-off, like, the convenience of voting from home versus, so like the process of going to some polling station. And I've sometimes wondered what the best system is. And I do think there's an argument actually for internet voting and so like remote voting, which is, you know, it's true if you have a polling station in ideal circumstances, you could have like, that to be a controlled place and prevent coercion. I think in practice, though, what you see is actually there's quite a lot of coercion taking place at the polling stations, right? I mean, if you go to a polling station, there's some guy standing with a machine gun, you're probably going to vote whatever they want, right? Also, if you have a polling station, maybe the authorities are just afterwards, going to throw out all the paper ballots and use their own paper ballots and count that, right? So there might actually be situations where, while in theory, paper balloting might be secure in practice, maybe it's actually internet voting that's the more secure version and the most coercion resistant type of voting.
Yeah, it's a new generation that's coming along. So I'm sure once existing generations go, then a new generation will just see mobile phone voting and smartphones as the way forward. So one of the problems that we have, and cryptography's been around for nearly 50 years, if you think the RSA was the first public key cryptography method to introduce digital signing. In nearly 50 years, we haven't really advanced the legal certainty of digital signatures. So we believe in them, but we still don't have really an infrastructure where if I digitally sign something, it's the same as my wet signature. I still put my nom de plume on documents and so on. I still have to sign. I can send a GIF of my signature to someone. They create a PDF, and that's seen as legally binding. But the EU is really going to change that, perhaps. In the UK, we're introducing digital identity, and I think it's going to have a difficult time because the last time in 2001 it was blocked because it was seen, one blog post stopped it because it was seen as a spying network for the government. So the UK is moving, but obviously the EU is moving big time. We now have EID for every citizen, eventually every business, and so on. It's bringing together countries, knocking down silos and so on. But the great advancement is that we have EIDAS too, which I think for the first time will have a legal certainty around digital signatures. But it's such a contentious area, digital identity and what's revealed and so on, and signing things and so on. What's your viewpoint on digital identity and the usage of these signatures?
Yeah. 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 So I think there are two aspects to digital signatures, and people sometimes mix those two up, right? One is the security aspect of a digital signature, right? And clearly nowadays, it's so easy to copy somebody's signature and put it in a document, right? So, sending a photo of your signature on some document, right? Doesn't have any security,
Brilliant.
you
Yeah.
know, properties at all, right? Anybody can forge that, right? So that just doesn't make sense from a security point of view. But I think the main application of digital signatures or signatures in general is not the security aspect of it. It's the agreement that, here's a point in time where before we were just discussing and so forth. But, as soon as the signature is like, now we're not just discussing, this is really what we want to do, and we agree this is what we want to do, right? And for most applications, right, I think people are not disputing whether you signed or something, right? It's more like, what did we agree to do, right? So it does serve that point in time, like, at that point, this is really your intention, that you want to agree to this kind of thing,
Every
right? And I
page,
think this
every
is why
paragraph, every word.
the
Yeah.
yeah. So I think this is why that system has arisen and why it actually does work for that purpose, right? Why does it? Because you should ask the question like, if it's so stupid from a security perspective that I send a photo of my signature, why is this still working? Why is that not just completely real, have been not realized it's broken? It's because it's really the other purpose. It's like, just saying this is a point in time where, I definitely agree to this, right? So, and then, I think it's great. I mean, I have used digital signatures in the past in Denmark, so like rolled them out some years ago. So there are some contexts where you can use digital signatures. And I think it's sort of like getting there and getting more common, right? And it certainly is more practical to put in a wet signature on a document. I have to say that, I travel a lot, and being able to sign something from a different country, and so forth is really a big convenience. So it's great to see that, the security aspect is also now starting to come along and work.
Yeah, but obviously digital identity, is it a good thing or a bad thing? I mean, should we really be putting cryptographic methods? I know that Jan Kamenisch had methods where you could take a signed document with my date of birth, my age, my gender, and so on, and then I can mask out part of it. So should really governments be? I know in
Yeah,
COVID we
yeah.
we we really advanced with green passport, a lot of great methods, but governments seem to have forgotten about some of those things. So where could cryptography help with that type of thing?
Yeah, so I mean, so this also touches on zero knowledge proofs, right? And what people are doing right now, right? So there's a lot of places in the legislation, so like the, know your customer legislation that, you have to check, the identity of people you are interacting with and doing business with and so forth, right? And the traditional processes, you go somewhere to some uh, data processor and you show them your passport and they look at you and look at your passport and say, yeah, yeah, you are who you are. And maybe you give additional documents to prove that this is where you live and things like that, right? And really that is a cumbersome process. And again, in some ways you're disclosing too much information, right? And people are now starting to construct, zero knowledge proof for all these kind of things, logins to something, proving who you are and knowing that you're a legitimate customer and so forth, right? And you can construct proofs that disclose exactly what, whoever, say, your bank needs to know without disclosing any other information, right? That you are a citizen of whatever country you are of legal age, so like this is your address and things like that, but not disclosing more than that information. So I think this is exciting times. I think the technology is there, and to a large extent, the issue is often that the regulation moves slower than the technology, right? So we then have this battle of getting legislators to approve of this construction as well.
Yeah, and I think everybody needs to get involved in this debate because every single citizen will have a digital identity and they need to have some, we need to have a grown-up debate in each country about how things are actually used, and it shouldn't just come from the
Yeah,
government to
yeah,
say this is what we're going to
yeah.
have.
I definitely think there are risks there, right?
Mm.
So there's been a lot of debate recently about the CSAM, right, and the government wanting to
Yeah,
monitor everything you're chatting about in your apps, right? Which I think is a very dangerous thing. I can sort of like definitely see sort of like the reason you want to protect children, right? But it is a technology that goes way beyond that, right? And so the really honest debate to have about it is like, what are all the things that government can do with that access to your what
yeah,
really ought to be your private data, right? And yeah, I think that's very worrisome. Even if you like live in a, say you live in a democratic, friendly society where, and the authorities are really competent and know how to protect the secret key, and it's unlikely that, somebody would hack the authorities and get access to so like the powers that the state has, even then I would be really worried because you don't know whether, 10 years from now, it's still going to be a fantastic democracy or somebody else has,
yeah,
with authoritarian tendencies have come into power and suddenly they have this tool ready available to them to spy on everything that their citizens do.
yeah. Estonia have probably came closest to that. I think they had a problem with RSA, which wasn't their problem. It was to do with another library, and they coped with it. It could have crashed their whole system, but they got around it because they believed in digital identity as a core to their economy and the importance of digital identity to their country. I think the EU will hopefully follow much of the approaches of Estonia, hopefully, for that. So elliptic curve cryptography was a slow burner as far as I can tell. So we have Victor S. Miller and Neil Kobolitz creating it. It never really went anywhere as far as I can tell. Took a long time. And then Satoshi Nakamoto came along. There was obviously the paper from Vanstone uh, and Menez that outlined ECDSA. It was basically taking DSA, which is a horrible, horrible, horrible uh, method of signatures with discrete logs and made it elliptic curve. And then Satoshi Nakamoto came along and adopted it for Bitcoin, and then we have Ethereum. Vitalik Buterin comes along and says there's an even better blockchain. We're going to adopt this ECDSA. So we're kind of locked in there, and we're now locked in with this EVM and so on. And I think you published work on the ECDSA signature, which is obviously the core of Ethereum, and that's the most trustworthy element overall. So, what were the key issues that you found with the ECDSA signature?
Yeah, so this is when I was working at DFINITY, and I was working with amazing colleague Victor Shoup
Mhm.
on this.
Yeah,
So
should yeah, yeah,
so like the issue that we faced was that we needed to have a way to have these distributed keys, right? And um, so exactly the like the key splitting and secret sharing we were talking about before, that you want to have this kind of thing. And what we were building was a service that could create these ECDSA signatures, right? In a threshold manner, so in a trustworthy manner where no single entity would hold the whole secret key, but they could collaborate and construct digital signatures. And we built that for ECDSA signatures. It's not the most practical signature scheme. We would love to do it for Schnorr signatures instead because they are more efficient, more amenable to these kind of techniques. But, well, because Bitcoin and Ethereum and so forth were using ECDSA, that's what we had to build for, right? So that's a standard that the world has converged on. Okay, so there are a couple of things in this kind of service. So the first thing, it's nice instead of sharing a million different keys to just have one master key that you have a secret sharing of, right? It's just much easier setup if you have to do it once instead of doing it a million times. And ECDSA signatures do have the property that you can have a master key and you can derive other keys from that master key, right? So basically saying, hey, there's a master key, now pick some offset that
seed.
maybe depends
Yeah,
on my name and other kind of things,
yeah.
right? And then, I'll create a public key which is specific for this purpose of this person, or whatever it is. So that's one nice property of ECDSA signatures, that you can do this kind of key derivation and derive other keys in a deterministic way instead of having to create completely new key from scratch and secret share it and do all that complex cryptography. Um, the other thing is when you create this kind of service and it's a multi-party computation, you have many parties because no single party holds the secret key, right? So they have to come together and jointly compute the signature that you want from this service, okay? And this is a multi-round protocol. So typically what they do is they first compute something called a pre-signature, and then they compute the signature, right? So it's like a two-step phase. The second phase can be quite fast, but the first stage is a bit cumbersome. Okay. So what we were exploring was, okay, what if you have ECDSA signatures in that context, right? What are the security properties you want? Well, you want it to be, safe to do these key derivations, right? You want it to be safe to generate these pre-signatures and, use them to construct the ultimate signatures, but also sometimes maybe something goes wrong, you just have to discard a pre-signature. Okay, and what we showed is actually, especially with pre-signatures, actually, yeah, it's not quite so safe always to have this kind of thing, right? So the question is, okay, then what can you do about that? Okay, and we came up with some ideas. One is that you don't use a pre-signature just as it is. You actually do a re-randomization step, which is cheap and easy to do, right? But gives you additional security. We also found a way to do the key derivation in a different way that would give you stronger security guarantees. So part of it was coming up with these new techniques that could increase the security, but still at the end of the day, just give a user an ECDSA signature on whatever they wanted to get signed. And then we built a model in which we could analyze that. So a new framework and the generic group model, but adapted to the specific elliptic curves that we're using there. So a more fine-grained security analysis of exactly these kind of different combinations of key derivation and pre-signatures.
That's good. But I mean, there are some blockchains that use EDDSA. and obviously it makes it easier to scale. But for this EVM engine, then ECDSC is the only show in town, and
Mhm.
it's really difficult to create this distributed key system for signing. And I
Yeah,
think some
yeah.
papers have been published, and they've found there are even been weaknesses in that. So I think there's always a risk when you're implementing these distributed key systems. So I think you've worked on universal composability frameworks. What are they and what's their advantages?
Yeah. So, okay. So if you think of a traditional cryptographic scheme, typically it's analyzed sort of like in a standalone setting. So you're saying digital signature, how do I sort of like reason about the security and that nobody can forge a signature on somebody else's behalf? What the universal composability framework says is really that, systems don't exist in isolation. They exist in sort of like in combination. You have like, large systems that are built of different components, right? So can we formulate a security model in which if you can show a component is secure in that model, then you can actually compose it safely with other things and get a sort of like a combined system that is secure. So that's the universal composability framework. It says basically, yeah, universal and it can be composed with anything. So roughly speaking, I'm cheating a little here, but roughly speaking, the intuition is that if you can prove that your cryptographic scheme is universal composable, it means it's very easy to go and plug in these different contexts. And sometimes you pay a price for that. Sometimes to have a universal composable secure system, then it is a little more expensive to run than one which is just standalone secure but doesn't have this universal composability property. And I've specifically looked at this in the context of zero knowledge proofs, so like defining what does it mean that something is an universal composable non-interactive zero knowledge proof, and showing that this pairing-based technique can actually give rise to universal composable non-interactive zero knowledge proofs.
It's tough because if you look at an application like in the finance industry, you're now looking at all of the primitives, you're looking at all the interconnections and things like that. So I think isolated a protocol could be looked at to be able to be composed down and to make sure everything is secure. But then the complexity of a digital asset trading system and all the interconnection is difficult. But I think we should be striving towards making sure that everything, because you just need one little problem in this one little thing that is wrong, and it could bring down the whole infrastructure of our world and the whole world of finance. So I think it's a really important area. So there you are. You've done your PhD, you've been an amazing researcher, the papers are just fantastic. Test of time is the way that you can tell a great researcher because basically a paper's been published and it's just not in the next year or two. It's not an incremental change, but 5 years later, people say, wow, this has changed everything. And you did that twice. And you're a professor at a world-leading university in an amazing city. Uh, and then you jumped. Not half jumped, but you jumped. I know that you still have your linkages with the university, perhaps, but you've jumped from academia to industry. Why?
Yeah. I think it was largely sort of like a desire to try something new. Okay, so as I have been for most of my career, I did my PhD with a company, Cryptomathic.
Hmm.
So that was sort of like in an industrial context. But since then, I've been at universities and in an academic context, and I did have sort of like curious to see what's on the other side, right? And so like seeing the world where you really meet the users. And at some point, when I was at University College London, I got the opportunity to try something new, to join DFINITY. And I had just, wrapped up, had a big grant. So like we wrapped up that research and concluded that most of my PhD students were graduating. So it was sort of like, a very clean point in time to sort of like think, okay, what's next? Do I continue in academia? Do I try something else? And I decided to take the jump. It sounds like a big jump, but in all seriousness, right, in academia, it's usually very easy to sort of like get a year off and try something else. And so I took the jump, but I still had the option of going back to academia if I wanted to. And it took a couple of years before I said, "Oh yeah, now I've taken the jump, and also like give back my position to UCL so that somebody else can fill that professorship." Um,
Yeah, I
so
think
yeah,
it's quite common for most of the professors, leading professors I've talked to. They've typically got a foot in both camps. They're working with companies and so on. Some decide that a spin-out company isn't enough. They need to be going to a company to be able to get their impact. But if you look at organizations like IBM, Google, for example, the role that you have as a research scientist in those companies is probably just the same without all the admin and the grant writing and all the things. I suppose it's the
I
teaching
think
element that you're missing. That's the one thing that you're not
yeah.
interacting with students as much.
Look, I think that depends a lot on the company you join because
Yeah,
research labs in industry, they're not all the same. They're all different.
yeah,
In a lot of the research labs, right? I mean, there are a few places where you just go and do whatever you want in terms of research, but most research labs will sort of like really want something that you can use in a product at the end of the day, right? And that has been my experience, after leaving academia, that I've been at places that it's not like you can just do whatever you want. No, you need to do something that brings something to the bottom line of the company and goes into the products that the company's producing. And you could say that so like also part of why I wanted to join industry was to experience that and build some concrete projects. So there's things I miss from academia, right? I do miss the freedom of, you can do research on anything you want. Um, I mean, there's still pressures in academia. You also need to get grants for your research and things like that, right? I do like teaching, so I do this teaching now. I do sometimes miss that as well. I mean, really, it's research. That's my passion. So that's also like the main part of the considerations.
yeah. And obviously AI has been around for I don't know, more than 50 years, 60 years. It's been around for decades and it didn't move that much. And then a little paper from Google on Transformers in 2017 changed the world really of AI and introduced the concept of having templates and probabilistic answers based on training. And we get the concept of large language models and so on. And it seems to be changing virtually everything in our lives. So this is a big question. Where's it going and what's it likely to have an impact on in the future?
Yeah. Okay. So I think AI is going to completely change the world
Mm,
that we know. I think it's underappreciated how impactful AI is going to change, and I think we're seeing sort of like shift where humans were the smartest on the planet to something where AI is going to be the smartest on the planet, right? And that's going to have a tremendous impact on all of us. And I think there's sort of like different layers of this. So let me see. So first of all, okay, where do we stand in AI right now? Um, and I'm sometimes surprised how little people are aware of that. And even inside technology and even inside science, people are not really coming to grasp with how impactful it's going to be, right? But what we're looking at now are, you know, we have billion-dollar investments, right, in companies, okay? And their stated goal is to build artificial superintelligence, right? We're not talking about like a little incremental step. We're talking about creating thinking that is vastly better than all of humanity combined, right? So that's like going to be an enormous impact, right? That's going to have, right? And it's very hard to imagine kind of technology that's going to come out of that, but also like what kind of society and so like what kind of existence that humans are going to have after that. And we're talking about a very short time horizon, right? I mean, if you look at what are sort of like the leaders of these research labs predicting, right? It's sort of like in the range of 2 to 10 years or something like that is the horizon, right? It's very difficult to guess and figure out exactly what the time horizon is, right? But it's very few that are saying that it will be 20 years into the future. We're really talking about like, something in the ballpark of 10 years or less, right? Okay, so what is that going to change, right? I mean, it's going to change everything, right? I mean, so let me start locally, right? What is it going to change for cryptographers, right? Well, we will now have algorithms that are better at coming up with cryptographic schemes, better at reasoning about the security of them, better at attacking these schemes, right? So I would expect that in 10 years' time, I'm going to be out of a job, right? I mean, why use me when you have a better researcher? And that also then sort of like makes me think a lot about it. And I don't have an answer to this, right? But so like, what is the contribution that is left to make, right? Which really makes a good positive impact on the world, right? Going forwards, right? When you know that, it's a bit like, if you're a professor and you have like, you have PhD students that are much, much smarter than you, right? And you know that, in a few years they'll graduate and then they will just take over your field and they're just much better than you, right? So imagine something like that, right? So it's the extreme version of that, right? Then you can apply that to sort of like society in general, right? I mean, what is the labor market going to look like? Well, it's going to be completely different, right? But I think people are not appreciating not only that is going to be different, then people are thinking, well, we'll have universal basic income and things like that. And so like everybody will earn a salary and that's going to work out. And in principle, it could be, right? I mean, you could imagine we just get better technology. We have, now we will have even better way of using the resources on the planet. Everybody should, if they share in this, then everybody is better off, right? Um, but it also raises questions like what is actually going to remain in this kind of world, right? Do money still make sense, right? I mean, money is something we use to pay other humans to do some things or give us resources, right? Does that still make sense when it's not humans, but it's AIs that are interacting? Not quite clear, right? Maybe it is, maybe it's not. And then I do worry about the risks that are involved in this. I do think there's a fairly significant risk that, we will just all die because of, something goes wrong here, right? There are many things that could go wrong, right? I mean, it could both be something where humans are involved, like say we evolve military technology beyond recognition, right? And then, we just kill each other. Okay. It could also be that, we have some misaligned AI that suddenly, it has its own will and, just does something that the AI wants and which is not good for humans, right? So I think there's a very big risk that we will die, all of us, because of AI. And nobody knows how big that risk is, right? So that's really hard to say. But it's very um, and then I think I think there's a um, I think people, underestimate also or overestimate how much the societal structures we have now are going to survive and make sense, right? So one of the discussions, for instance, that is now taking place is like, should we sort of like pause AI and try to, think more carefully about the safety of AI? And I definitely think we should, right? But, one of the arguments against it is like, in the US, you will say, hey, China is racing towards AI. And in China, you might think, oh, US is racing towards AI. Now we'll build up this, race of AI, right? Um, and I have to say, I'm a little skeptical about that reasoning because there's an underlying assumption that, as say an American citizen, right? I'm not American, so this doesn't apply to me, but at least maybe as an American citizen, you said, oh, this is good. If US wins, then I also win. And that's not clear to me at all, right? I mean, it's not clear that in a post-AI world that, that a nation state such as the United States makes sense, right? It's not clear to me that if you're an American living in Iowa, that, whoever built the AI who's living in California actually cares about you, right? So, so it's it's very hard to predict what the world is going to look like. It may turn out very well and be a benefit for all of us, right? It may turn out to be a catastrophe for all of us, right? And I think people, so if you look at people who do know about artificial intelligence, it's also telling. There was this study that was looking at, so like, what are the safety opinions of people who really work in the AI space and know AI, right? And you could see a correlation. The more people knew about security, the more concerned they were, right? Now, it could be correlation, right? We don't know, is that causation that, the more you know about security, you can judge better and more aware of your risk, or is it more like, well, the more worried you are, the more likely you are to read about AI safety, right? But I would say that I definitely strongly feel that, and I think this is uh, coming from a background as a cryptographer, right? I know, so like, that we have, horrible cybersecurity on the internet and the world in general, right? Just because it's very complicated to build secure systems, right? So correspondingly, I know, if you're trying to create a safe system that controls an AI, that's going to be very hard to build, right? And I just think it's a big challenge, and people who don't work in security, they do not appreciate how difficult a task that is, and how likely it is that we fail in it. And then on the flip side, I'm trying to think about what can you know, do about that, right? And I do think that people who work in security and cryptography have a special role to play here. So, and the role is, I think, first of all, we need basically theoretical reasoning about security, right? And this is exactly the kind of thing that we do in cryptography. You need to have build some models for what does it mean that a system is safe, right? And to have the tools to reason about that. And that's exactly what we do, right? And I think it's exactly what we need in terms of, how AI is going to evolve in the future. So I do hope that in general, cryptographers and other people working in security will pick up that challenge and come up with ideas. It's difficult to say what are the ideas, and it's much more complicated world than, cryptography looks at these very nice, clean mathematical problems, and even there it's hard to reason about it, right? Now we have like much more complicated system we need to reason about. But I do think that we need theory for AI safety, and so like really dig into, you know, figuring out a path forward that does make AI safe.
Yeah, it's a difficult question because now you've got agentic AI, which is having hold of your encryption keys and your passwords. It actually knows about you and your next of kin and what they like and everything. It's learning everything about you. And have we worked out how the privacy issue of that works, how the security of the data works? I don't think so. We're almost like running towards one or two companies on the west coast of the US to be able to do this, and we just hope that it's all done correctly. But it's the mighty dollar that is the king here. It's not necessarily your privacy, your intellectual property that they care that much.
Yeah,
I wrote books, and nobody asked me. Google didn't ask me if they could scrape all my books and find out all my knowledge and so on. So the whole world of
yeah,
intellectual property is almost like falling apart.
yeah. I do think that we have to think about what are the priorities of the concerns, because there are many different concerns you could have with AI. And I think people say AI safety and then they mix everything together, right? So they're concerned about privacy and so like what does AI do towards a particular individual, right? The concerns about society and say, will there still be a labor market, right? And then the existential risk and, will we all die from AI? I do think these are different concerns. They're not necessarily the same concern. It's not necessarily the same kind of things, solutions we need to figure out to resolve those kind of questions. And I think, okay, I'll give sort of a hot take here. Okay, if I have to choose between, existential risk and risks to privacy, I think that existential risk is the important one. And if you could come up with some way to make AI perfectly, safe for humanity, but it really violated privacy, I would choose that option, right? So
And there's a real job of a kill switch engineer. I think OpenAI had an advertisement, and one of the attributes, one of the skills was to be able to pull the plug,
yeah, yeah.
or to throw a bucket of water over the servers and so on. But obviously, if you extend that on, why can't AI actually move out of its sandbox and move somewhere else that has other electrical supplies and so on? And why doesn't AI come up with its own cryptographic protocol so that it can actually communicate? So that's the worry, and you got to worry that people who are designing these things just now aren't really taking these safeguards, the guardrails into account. They've got the ethical things sorted out to a certain extent, not quite there yet, because they make sure that what you get is has diversity in it and ethical and so on. But I don't think they've looked at, as you say, the real top level societal damage questions yet. If they're controlling nuclear weapons, then what's to stop them from saying that humankind is a cancer on society, and the only way to get rid of wars and badness is to get rid of us. So I think it's such a big question mark just now.
I think it is. I do feel, I mean, so I don't have any answers in this
Mm,
space, but I am thinking about what
mm,
would be the right approach. I do think that sometimes I have the feeling that I'm working on all of the kind of things that are actually relevant in this context, right? Because I'm working in cryptography, which, really is about like how can you design a theoretical model of, the security of the system? How can you reason in advance about the system such that they cover all the attacks, not just, the attack that, somebody comes up with. And that's what you need to do, right? I'm working in blockchain. You can also ask, so like, what is so like the ground truth that we can rely on? And blockchain is, something that might be able to build so like a very stable foundation, right? Um, I'm thinking sometimes about game theoretic incentives, and I think this it's also a question of what is the incentive of the participants, right? Because a lot of this, is it going to be US or China that comes first and potentially kills us all, right? So it's sort of like a race to the bottom. Um, but it's really a question like, what are the game theoretic incentives, right? It's like a tragedy of the commons kind of problem, right? And in the blockchain space, we are designing incentive systems, and maybe that's, exactly what we should be doing here, right? To sort of like rethink society and design incentive systems such that the people that are building AIs actually have incentives that are aligned with all of humanity. Um, so I mean, and
Yeah.
certainly also like just being realistic about, security and the many ways, right? I mean, people do have these kind of naive hopes that, you can design a kill switch and then everything is great. If things start going wrong, you just, you know, shut it down, right? And press the off button, right? And, that's not how the world works, right? I mean, and there's so many ways we know as cryptographers, there's so many clever ways that you can circumvent security mechanisms and so forth. It's I think that's just not going to fly. It really is a super challenging question to make AI secure.
Yeah, and I suppose we haven't really fixed our computational infrastructure. If you think about what we really want to do is to take the laws, all our ethics, and codify them into a smart contract. Okay, we're doing that with Gen AI. It's very good at indexing and taking a policy document and distilling out. But can we take that next step into codify? So that is where we create this trusted computing infrastructure. This is the laws of the land, and this is what should be implemented, and it's fair on everyone, and everyone knows what it is. And that's the smart thing about a smart contract is that there's nothing secret in there. It's everybody can see it, everybody knows what it is, and so on. So I suppose it's that jump now to take the power of Gen AI and to now make it, to codify it, to mathematically define it for certainty. Otherwise, it will just go wild just now. It's strange when you think that machine learning grew up with thousands and millions of lines of code, and then someone somewhere decided we only need a few lines of code. And what we need is to learn just like we do as humans. I think the other thing is that if you bring children up to be good citizens and you don't swear to them and you teach them good ethics and so on, then you actually end up with good adults. But if you teach them bad things, then you can end up with bad AI.
Um, I'm a little skeptical about that actually. And the reason is that, I mean, if you think about different dictators, Stalin, for instance, right? He was actually, a very principled person. He suffered a lot for, a cause he believed in and so forth,
Mm,
right? And, when he actually came into power, he was like, horrible, brutal dictator, right? Killing millions of Soviet citizens. So I don't think it's so much necessarily just the upbringing. I think a lot of people have like the potential to do good things and bad things in them, and it's really about the circumstances they're placed in. And I have to say that, I'm whenever there's, you know, authoritarianism is on the rise, I'm concerned because you might even have somebody like this is like the most brilliant leader ever, does great things for the economy and so forth, right? But you don't know that that's how they're going to be in 10 or 20 years from now, and you don't know who they're going to put in as their successor, right? So, I do look at, the people, the CEOs of various AI companies, maybe the model that we'll have in the future is that, it's the CEO who's ruling over the AI and ruling over the world, right? And would I want any of them to be so like the world leader? And the answer is no, even if, I mean, there might be some of them that, I think are, seem like nice moral
mm,
people, but, I just don't trust that that's going to last if they come into
yeah,
power. I mean, sometimes
yeah,
people just develop a different personality when they get a lot
yeah.
of power.
Yeah. But I suppose it's the data that you're training your Gen AI on. If you train it with bad data, it can be evil just as much as being good overall. And some of the data sets I've seen aren't very diverse in terms of what they output. If you ask them for a photograph of a cybersecurity professional, it will be male, white, with glasses and looking rather geeky and so on because it hasn't trained on a diversity of data. So I think we've got to understand really how we train these Gen AI models to make sure they are diverse and ethical overall.
Um, I think it's a super challenging
Mm.
question, right? Um, in particular, whatever moral values we have in society now might
Yeah.
not be the same, right? It's like, I wouldn't want the moral values of 200 years ago to be the
Mm.
ones that are prevailing in society
Mm.
today, right? So we both have to have a system which is adaptable, but then it shouldn't go in the wrong way, right? Whatever that means. So I think that's a very tricky thing. And I do think there's also this tension of like, do we seek out truth or not, right? I mean, which is also something that's come up in sort of like a scientific context. What can you do research on? What can you not do research on, right? I mean, so you brought up the question of like a professor, white male, and so forth, right? But
Mm.
maybe that data reflects the world it is. Like, 50
Yeah.
years ago, it, there were universities where, you said, hey, professor has to be male, right? It cannot be possibly be a female, right? Which,
Yeah.
you know. is ridiculous for us
Mhm.
now, right? But so it's sort of like, should a model represent, actually the world as it is, which has biases and things we don't like and so forth, right? Or should we try to, design it in a different way, right? And then, who gets to dictate what the different way and what the norms of society should be. So, there's a lot of challenging questions like that, right? And I
Yeah.
think I think people are grappling around that, and I don't see any good answers that anybody's coming up with there.
My final question. Thanks so much. I've taken so much of your time. I apologize for that, but it's been a great discussion. And really, we've went full circle now nicely with AI and integrating with cryptography is a great approach. And for any researcher looking at this, that's a great thing to start to be. If you draw a Venn diagram of AI and cryptography, the bit in the middle is where we really need to be, and we need to work together with lots of different types of skills uh, overall and build teams that aren't just cryptographers. We're looking at society and so on. This is a big question. So my last question is that if you could change, you've had such a diverse career and it's had lots of different routes through it. So if you could change one thing about your career, what would it have been?
Yeah, that's a tricky one. I'm trying to think about like, the path I've chosen. I mean, I'm very happy that I got into zero knowledge proof. I really do enjoy doing research. So, I know that a PhD is not for everybody, but it's definitely the right choice for me personally to do
Yeah.
that. And getting into this field. I think a lot of the success I've had is also luck, right? You sort of like hit on the right topic, you hit on, so like you're in the right spot and you see, oh, this idea and this idea. And if I combine them, something good comes out of it, right? I certainly think the adoption of my research that Groth 16 became a big thing. It was really Zcash that was incorporating into their protocol, and then a lot of other people use their libraries and so forth, right? So I think, I've also just been lucky, right? I mean, and I wouldn't want to change that, but it's sort of like it's not very useful advice to give to other scientists, just, be lucky, right?
Be more lucky.
So yeah. Um, I think, there may be a couple of things that I felt that um, I missed. I think in terms of teaching, I mean, so I've sort of like gone into industry now, but actually, I think if I had sort of like a bit more industry experience and exposure beforehand, it would have been useful for teaching because, most of the students I have, they're not becoming academic researcher, right? They're going out into industry afterwards. I think it's sort of like useful to have put in that camp, even if you're focused really academia and doing teaching to students. Another lesson I've sort of like learned very, very slowly and probably not super good at is sort of like advertising your own things. I've been more like, I want to do some cool research and I'll write a paper and then, I'm done, I've published it, right? And reality is now that people do a lot of, promotion. You have to also not just, publish your research, but you also, have to go on and telling people about sort of like what is the core piece that you're adding to the world here, so for them to pick it up. So I do think there's some, I mean, people, lots of people know across 16. There are some other pieces of work that I'm really proud of, and actually had a lot of influence in the field, but people are not aware of that history, right? So um, but overall, I don't think there's too much I want to change. I think I've been very fortunate and very happy with the run I've had so far in cryptography.
That's good. And you say luck. It's not really luck, it's having a good eye for reading a new paper and determining that this has the potential to be something amazing. I think it's easy to take the bell curve and everybody
Yeah,
is into the research area and the research area is so active. That's not when you want to get into the research
yeah,
area. And the
yeah,
bell curve means that a subject is dying in the end. But the trick of a researcher is to get in right at the start to be able to identify that something is really taking off and to see the potential. So I don't think it's luck. It's actually knowing that something, as you said, you went to a conference and you saw one paper that wasn't in your field, but you translated it. So to me, that isn't luck. That's really understanding how you take someone else's work and bring it and advance it.
Look, there's the expression that luck favors the prepared, right? So certainly, I think a good scientific advice is to, think about different problems. So you have sort of like a portfolio of places where you can get lucky if the right idea
Yeah,
pops up, right? So definitely think that's part of it. But I
yeah,
really do think that luck also, I mean, as a researcher, you have to go into the unknown, right? And you don't know whether there's something, that you can find or not find in that area. And, not everybody's lucky. They do excellent research. They try their best, but they just picked whatever the wrong direction, right? And it didn't pan out, right? And I know plenty of people that I think are really brilliant thinkers, but, just picked a topic and it turned out that wasn't quite the thing they hoped for in that area.
yeah.
So yeah, bit of
Well,
both.
thank you so much. I've taken up nearly 2 hours of your time, your precious time, but I think we've covered so many topics, and hopefully, uh, early career researchers and PhD students and people who are doing MSCs and undergraduates might want to consider a career in research, either in industry or academia, and to really follow what you've done. I highly recommend anyone to read all your amazing papers. They typically get over 200 citations each, and there's so many of them. But you've created such high impact papers, not because you sold them, as you said, because people have picked them up and seen the opportunity and have taken your name and given it to a method. I think that's the great thing in cryptography is that we're still using the Diffie-Hellman method, we're still using the reverse Shamir and Edelman method and so on. And we're very good, Fiat Shamir, of talking about the original seed of the idea and adopting that in a personal way to show that this isn't a generic technology, but we're going back to that first paper. And I think you've created so many starting points. You're typically the first author on all of your papers. A lot of your papers are sole authors, which is quite unusual. And the time that you get tens. Some of the AI papers
Yeah,
have got
yeah,
thousands. I
yeah,
I reviewed a paper the other day for my student, and the citation went on
yeah,
for two pages,
yeah,
and you
yeah,
go, that's just crazy. That doesn't
it
come out
is. Yeah.
the minds of all these people. So I
Mm.
think you've really contributed so much. So thank you so much, and I hope you have a great rest of your day. And hopefully I'll speak to you soon. Thank you.
Thank you, Bill. It's been really a pleasure to talk to you.
It's great.